Hi y'all, welcome back. So now where we'll talk about problem C. So problem C, they ask for the momentum balance in the actual direction, right? So let me write down. So momentum balance in the axial direction. What is the actual direction? Is the Z direction. It's in Z, okay. Okay. I write like a 7, that's why I need to delete. Okay. So which equation will be used? Again, we will be using equation 5.7, page 282. So what does this equation say? It's a Navier-Stokes equation, but in the axial direction, right? It say rho times what? Times the change of velocity over time, or the partial of uz over time, okay, plus ur times partial of uz over partial r plus u theta over r times partial of uz over partial theta plus uz times partial of uz over partial z. Okay, tips for y'all when you write these type of Navier-Stokes equation. It's always a good idea to have a long sheet of papers. Even better, I would recommend everyone to have a tablet. You don't have to have a tablet, but if you do have a tablet, please write on it, and then you can copy paste this equation from places to places, because the equation is usually very long. Like for example, you see this term is only take one of the pages on the whole line in my tablet. Is not even the complete equation yet. Okay, so let's continue. So it equal to negative partial pressure in the z direction plus mu times 1 over r times partial r of what? Of r times partial z over partial r. Okay, plus 1 over r squared times partial of uz over partial theta square, mean it's the second derivative or the second partial derivative, plus partial of uz over partial z square, mean this the second partial derivative. And then lastly but not least, you have the gravity term. So it's rho times gz, the z components of the gravitational forces. Okay, so let's see which term can we cancel out from this equation. So we know that this is a steady state, which means that the velocity doesn't change through time. So the partial of uz over t right here cancel out because of steady state. Okay, the next thing we notice is that all these terms right here contain uz, and previously we had demonstrated that uz is 0. Therefore, all of these vanish because of uz equal 0. Okay, the next thing we notice is similarly, all these terms right here has uz, so it all vanished because you write uz equals 0. So here's uz equals 0. And of course there's no gravitational effect, so you can write no gravity effect. That's why there is no gravity in all direction, including the z direction. Okay, so what we have left, we are left with this guy right here. Okay, so you can say that partial of pressure over z equals 0. Okay, what does it say? What does the result make sense? You have to be careful because he usually asks that on the homework or exam. He always asks like, does the result make sense? Well, it does. So let me write down. Does the result make sense? Yes, it does. Why? because there is no flow in the z direction, or the liquid would spill out. Okay. All right. That is for part C. Now let's go ahead and move on to part D, which is kind of a little bit more interesting, as you will see. So let me write a problem statement for part D. So part D, they ask for the momentum balance for the azimuthal. Okay, this is just a term. It really depends, but in this case, azimuthal is the theta direction. Okay, so what equation will be used, and which page that? I hope that the page doesn't change that much from textbook edition to textbook edition, but right now I can tell you that we will use equation. So using equation 5.77, 5.75, page 282. Okay, let's see what it say. So it say that rho times, again we have the time, the partial derivative with respect to time, but now is in term of u theta, so u theta over t. Tips for you: if you see a forest of equation in the textbook, the best way to recognize directly which equation corresponding to the axial, azimuthal, or the radial direction is look at the first term. Okay, look at the time partial derivative, and the velocity right there is the good indication of the direction. So in this case you have u theta, right? So you know u theta, this is equation is talking about the theta direction. Okay, moving on. Now you can add ur times theta u theta over ur plus u theta over r times partial of u theta over partial theta plus ur times u theta over r plus uz times partial of u theta over partial z. Okay, equal to -1 over r times partial beta over pressure, not beta, partial pressure over partial of theta plus mu times partial with respect to r of 1 over r times partial of r times u theta over partial r. And then you can add what? You can add 1 over r squared times partial of u theta over partial of theta, but in this case square, which indicate it is the second partial derivative. And you can add 2 over r squared times partial ur over partial theta, and then you can add the partial u theta over uz square, mean it's the second partial derivative. You close the bracket and you add the gravity term, so it's rho times g theta. Okay, perfect. You have only the equation. Okay, let's see which terms cancel out. So we know that this is a steady state problem, therefore there is no change of velocity with respect to time. So you can say this term cancel out, due to steady state. Okay, wonderful. The next term, you can say this term cancel out too because you are 0. Okay, so you say you are 0. Wonderful. lastly but not least, no, that's not lastly but not least. We have a lot of things to cancel out. Okay, this term right here, you guys have to be careful. U data is not 0, right? But this term right here, the partial of U data over partial data is actually 0. The reason why we have is because of the continuity equation. Here, there you go. So this is the result we obtain from the continuity equation, right? Then right here, you can say this is completely vanished. So the reason why this term cancel out because partial U data over partial data is 0 in the previous analysis. So I write continuity equation. Okay, this term cancel out because of U are 0. Okay, wonderful. This term is cancel out too because UZ is 0. Okay, bear with me. This term cancel out because you notice something very interesting. You have we have the partial of U data over data is 0, right? Previously, therefore the second derivative of it also 0. That's why this is 0, and you cancel out the whole thing. Okay, this one cancel out because you are 0. This one cancel out. Is it cancel out? No, it does not. This one cancel out because no gravity effect. Because there's no gravity effect, so there's chi theta 0. Because, you know, all direction, chi theta, chi r, and chi z 0. Okay? Okay, unfortunately, let's see what term we have left. Let me go ahead and box it for y'all. What term do we have left? Okay, we have this term left. Okay, we have the term left, and we have this term left. Okay, so we have quite a few people left here. So later on, you see we make some assumptions. In the next video, you see we make some assumptions, and we will see how we solve the problems. Okay, have a good one. See you in the next video.